Okay, let's do the next application of a mean value theorem. So 4.17 theorem is also called the Bernoulli's inequality. Bernoulli's inequalities. There are two inequalities in terms of a parameter. So let alpha be a positive real number. And delta greater than or equal to -1. If alpha is between 0 and 1, including 1, then 1 plus delta to the alpha's power is less than or equal to 1 plus alpha times delta. It's less than or equal to. And if alpha is greater than or equal to 1, here also including 1, then 1 plus delta to alpha's power is going to be greater than or equal to 1 plus alpha times delta. Okay, so here, in both cases, we include 1. It's because when alpha is 1, it's just 1 plus delta on two sides. So it's equality. It's just you don't have a contradiction. Okay, alpha equal to 1 is trivial. It's linear. Alpha equal to 1. Okay, so the important situation is that alpha is either between 0 and 1 or alpha is strictly greater than 1. Equal to 1 is not that interesting. Okay. Okay, so the statement, the proof says the proofs of these inequalities are similar. Well, let's see how similar they are. Okay, so here let's follow the proof for the case of alpha. Case 1, alpha is between 0 and 1. Alpha is between 0. And then we define the function of x as x to alpha's power. Okay, then we have delta. Delta is greater than or equal to -1. Delta is greater than or equal to -1. So we have a number number c between 1 plus delta and 1. So far I don't know if which one is bigger, which one is smaller. I just say between 1 and delta, between 1 and 1 plus delta, there is a number c such that f prime of c is equal to f of 1 plus delta minus f of 1 over 1 plus delta minus 1 by the mean value theorem. Okay, so for the mean value theorem, you can use fb minus fa over b minus a, or you can use fa minus fb over a minus b. It's the same thing. So in that part, it's a symmetric. It doesn't matter which number is bigger, greater. But when you talk about intervals, you always put from 0 to 1, from smaller number to greater number. So that's why here it can be negative. If it's negative, 1 plus delta will be less than 1, right? So what is f prime of c? F prime of x is alpha x to alpha minus 1. So f prime of c is alpha c to alpha minus 1. Right? So what we get f of 1 plus delta is equal to f of 1 plus alpha delta c to alpha minus 1. Okay, so the denominator is delta. You multiply it by delta, it is alpha times delta c to alpha minus 1 is equal to f1 plus delta minus f1. You move f1 to the other side. Okay, so that's always correct. It doesn't matter delta is positive or negative. Now let's see the discussion. A delta is greater than 0. If delta is greater than 0, C is between 1 and 1 plus delta. Okay, C is between 1 and 1 plus delta. So C is a positive. But alpha, where is alpha? Alpha minus 1 is less than or equal to 0. Alpha minus 1 is less than or equal to 0. So C to power alpha minus 1, it is what? Okay, so here. Alpha, C is greater than 1, so C to 1 minus alpha, to any positive power, it will be bigger, right? So it's a bigger denominator. Means what? Means that's less than 1. Okay, denominator is greater than 1, the whole thing, the reciprocal will be less than 1. The reciprocal will be less than 1, am I right? Yeah. Yes. And then we multiply this inequality by delta by alpha. We get alpha delta C alpha minus 1 less than alpha and times delta. And then we add F1. F1 is 1. So we get F1 plus delta is less than or equal to 1 plus alpha delta. 1 plus alpha delta. Okay. Part B. Part B. Delta is between -1 and 0. It's negative. Negative. C is less than 1, but greater than 1 plus delta. But it's a positive number, but less than 1. Less than 1, the same thing. Alpha is less than 1. So C to alpha minus 1 is 1 over C to 1 minus alpha. This is like 0.1 stuff. It takes certain positive power. It's still negative. Sorry, it's still less than 1. You flip it. It's greater than 1. Greater than or equal to 1. Right? You flip a smaller number, it's bigger. So we have this. It's a C to power alpha minus 1 greater than or equal to 1. This is inequality, and in this moment, delta is negative. We multiply this inequality by a negative number. It becomes less than or equal to delta. Okay? Multiply inequality by a negative number. And then we multiply this by a positive number. You still have the inequality. Alright, so anyway, we get alpha delta C to power alpha minus 1 is less than or equal to alpha times delta. So we still have this. Right? We still have this. So this is the two cases when alpha is between 0 and 1. This is two cases when alpha is between 0 and 1. Delta is greater than negative, greater than or equal to negative. What you see here, we actually didn't use alpha is greater than -1. Why do we need alpha is greater than -1? Why do we need this? It's simply because when alpha is too negative, 1 plus delta, or not alpha, when delta is like, for example, -2, 1 plus delta will be a negative number. Then we have issue when alpha is a fraction. You take for example, a -2 to the power 1/2 something, you have problem. So we want to guarantee that the base is positive. So that's why base is non-negative. That's why this delta is greater than or equal to -1. We just want to make sure 1 plus delta is positive. Okay? So that's the only reason we set delta greater than -1. That's the only reason. Otherwise, in the process, you don't see that why delta is greater than or equal to -1. Okay, so this is a case discussed by the textbook. Now let's see what happens if alpha is greater than or equal to 1. Alpha is greater than or equal to 1. We do the same argument. Remember here delta is greater than or equal to -1, and then we have there is a c between 1 plus delta and delta and 1 such that f prime of c is f of 1 plus delta minus f of 1 over 1 plus delta minus 1. Okay, the same thing by the mean value theorem, by the mean value theorem, and then we get the same differentiation. The differentiation does not depend on the parameter, so we have this, the same thing. Now we have the case, the A, B, and then I put C. Delta is greater than 0. Then C is between 1 and 1 plus delta. And this time, alpha is greater than or equal to 1, so alpha minus 1 is positive. So C is a bigger number. You take a positive power, it's going to be greater than or equal to 1. You multiply this inequality by alpha times delta. Alpha positive, delta positive, so 1 plus alpha delta. F of 1 plus delta is greater than or equal to 1 plus alpha delta. See, here we only need we change the inequality. We change this inequality from less than equal to the greater than or equal to, because alpha is bigger. D, if delta is between -1 and 0, then 1 plus delta less than C less than 1, and alpha minus 1 is still positive. And in this case, this c to power alpha minus 1 is going to be less than or equal to 1. Less than or equal to 1, because the base is less than 1. It's a decreasing function. Okay, and then you multiply this inequality by negative delta. Delta is a negative number. You multiply the inequality by a negative number. You flip this inequality. Okay, and then you multiply it by alpha. Alpha is positive. You still have greater than or equal to case. So we get f of 1 plus delta greater than or equal to 1 plus alpha delta. 1 plus alpha delta. Okay, so they're consistent. So you see that actually that's why the textbook said they are similar. The proofs are similar. You only change the sign, change the inequality because of this alpha minus 1, positive or negative. All right. Okay. So this is the other application of the mean value theorem. Okay. So mean value theorem also has one important application. Another important application is the L'Hopital's rule. The L'Hopital's rule is a very useful and powerful tools to get the derivative, to get the limit. Okay, so we're going to try to prove the L'Hopital's rule. We didn't prove it when we studied calculus. Okay, this is L'Hopital's rule. What is L'Hopital's rule? Let A be an extended real number real number and I be an open interval that either contains A or has A as an endpoint. Okay. Suppose that f and g are differentiable on the interval I without A, and g of x is not equal to 0, g prime of x is not equal to 0 for all x in I without A. Suppose further that A, which is the limit of x approaches A, x belongs to I. It is equal to the limit x approaches A, g of x approaches A, x belongs to I. So this notation, it covers one-sided limit and regular two-sided limit when x belong to I. Okay, if A is an endpoint, x belong to I. Left endpoint, x will approach A from the right side. Right endpoint, x will approach to A from left side. So this notation will cover one-sided limit plus regular limits. Okay, if this limit A is either 0 or infinity, okay, and if the other number B, which is a limit x approaches A, x belong to I, f prime of x over g prime of x exists as an extended real number, then the limit x approaches A, x belong to I, fx over g of x is equal to the limit x approaches A, x belong to I, f prime of x over g prime of x. Okay, very long. We just try to get the proper setting, and then we get a conclusion. This is a conclusion. The derivative of the ratio is the derivative of the ratio of the limit. Sorry, the limit of the ratio is equal to the limit of the ratio of the derivative. I said something wrong. Sorry. The limit of the ratio is equal to the limit of the ratio of derivatives. Okay. Okay. Let's see the proof. We want to use sequences to evaluate the limit because of the sequential characterization of the limit. Okay, so let xn belong to I with xn approaches A as k approaches infinity. Okay, so it belongs to I. So by the sequential characterization, of limits its surfaces to show that fxk over g of xk converges to b as k converges to infinity, approaches infinity, right? So for whatever sequence xk approaches a, you can prove this, and then by the sequential characterization, we have the result. Okay, so now here we just in the proof, we assume that B belongs to R. B could be where it is. This B could be an extended real number, but to simplify the proof, let's just assume B belongs to R. If B is plus or minus infinity, you can try to prove it similarly, but in a slightly different. Okay. It says it will be the exercise, so it is also left to you as an exercise. We just try to get the main idea about the proof. Okay, so we assume B is a real number. B is a real number, and we know that G prime of x is never equal to 0 for x in I without A. G prime of x is never equal to 0. So by mean value theorem, what we know? We know that the g of x minus g of y is never 0. G of x minus g of y is never 0. Okay, let me see where's my page. Okay. Now let's see the situation. Because it's never equal to 0, so we can always put it in the denominator. Remember that. Okay. So let's study the case. Case 1, a is equal to 0. The limit of fx/gx are both 0. And this point A is a regular number, a regular point. Okay. If A is equal to 0, it has a limit. Once it has a limit, this point A is at most the removable singularity. So we can extend f and g to I union I union the point A by fa equal to ga equal to 0. Then fg are both continuous. Okay, so fg are continuous over I union AB, and differentiable over I but without A. So we still don't know the differentiability at point A. Okay, so remember that we have generalized mean value theorem, or the Cauchy mean value theorem. By the generalized mean value theorem, we have, there is you point a number ck between xk and a. Okay, remember xk approaches a, so between xk and a we always have a ck such that fxk minus f of a over g of xk minus g of a is equal to f prime of a ck over g prime of a ck. Okay, f prime ck is g prime ck. And remember here the denominator is never 0 when xk is not equal to a. And fa, ga, they are both 0. So we actually have this relation. ck is between xk and a. So the limit of ck, k approaches infinity, is equal to the a is fixed, x is a constant number, is a sequence, x approaches a. By the square theorem, the limit of ck is also a by the square theorem. Squeeze theorem. Okay. Okay, so let k approach infinity. So limit k approach infinity, fxk over g of xk. And this is exactly b. Okay, because this is equal to ck approaches a. Right? That's the simplest case in the whole computation, the proof, in the whole proof. Just because fa, ga, they're both 0, they disappear. So by coincidence, you do have the ratio of f and g is equal to the ratio of f prime and g prime. All right. Okay, now let's prove another case. Okay, so this is the simplest case. Case 2, we may not be able to redefine function fg so that it's continuous, because the limit at a could be plus minus infinity. And still, we assume this point a is a regular number. Okay, plus or minus infinity is not essentially important, positive, negative. So we assume that a is a positive infinity, just to make the computation simple. A is a positive infinity. Remember this xn converges to a. So x1, x2, x3, x4. So for each k and n in the integers, by the generalized mean value theorem, there is a ck comma n between what? Between xk and xn. Okay, so you have a sequence. Every two points, it's not always adjacent. every pair of 2 points, you can find a ckn such that what we have the following thing. It's a little bit complex. What do we want? Okay, so we want to compute Fn over Gn, right? We want to compute Fn over Gn, but we cannot directly subtract the same number from top and bottom, because this moment it becomes infinity. Okay, so we just cannot do that. So what we do is the following. We put fxk gn and plus fxn minus fxk g sub n. So we have this. And what is a generalized mean value theorem? Fb minus Fa over Gb minus Ga is equal to f prime of c over g prime of c. So we have this Fb minus Fa. We have this Fb minus Fa. So we move this to the right side. So it is equal to what? Equal to this one? The denominator is still 1 over g of xn. Denominator is still 1 over g of xn. And numerator becomes this g of xn minus g of xk. That's the denominator. And times f prime of ckn and g prime of ckn. Okay, f prime of ckn and g prime of ckn. And then you distribute this denominator into the bracket. You will have fxk over g of xn, and this one is plus 1 minus g of xk over g of xn times f prime of ckn g prime of ckn. Okay, and then you do the distribution. You see here, we want this 1 times this. So we have f xk g xn minus g xk g xn times f prime of ckn g prime of ckn, and then plus f prime of ckn g prime of ckn. All right. Okay, remember that. So what is the advantage of this formula? It looks very complex. What is the advantage of this formula? When n approaches infinity, we may assume k and n are sufficiently large. So this quantity is very close to b. This quantity is close to b. And here, this quantity is close to b. But this quantity, remember here we have two indices. This k index, first, it's sufficiently large. Ka should be sufficiently large. But once it is sufficient and fixed, it is fixed. Okay, sufficiently large and fixed. And then this xn, n is arbitrarily large. When n is arbitrarily large, g of xn will approach infinity. G of xn will approach infinity. So it makes this fixed. It's a fixed numerator. Fixed numerator over a arbitrarily large denominator. Fixed numerator over arbitrarily large denominator. Even though you multiply it by a constant b, but still it's a fixed number. Okay, so it makes this small enough you can ignore it. This small enough you can ignore it. You only leave b here, and this b is the limit of f(xn) over g of xn. Okay, so that's an idea. That is an idea. So here we see the concrete proof, the detailed proof. So let epsilon sufficiently small here, epsilon between 0 and 1, ckn will approach a as k and n approaches infinity. They have to be both approach infinity, then ckn will be squeezed to a. Okay, so we choose n0 such that for n greater than or equal to n0, this term f prime of a c, you see this, you already have k. K is this n0, sufficiently large but fixed. Sufficiently large but fixed. F prime of cn sub 0 comma n over g prime of a cn sub 0 comma n, and minus b is less than epsilon over 3, whatever, it's just epsilon. So it just means it's close to b. It's close to b. And g of xn converges to infinity. So there is n capital N greater than n0. If it's greater than n0, or it's okay. If it's not greater than n0, just choose n0. Okay, such that the f of xn sub 0 over g of xn, remember the denominator will approach infinity, and this quantity we put ups value, and the other quantity, remember this one is at the most, ups value is at most b plus epsilon over 3. So the g of xn sub 0 over g of xn times f prime of cn sub 0 n g prime cn sub 0 n. Remember here, this one is bounded. It's one bounded. So both are less than epsilon over 3 for n greater than or equal to capital. You already have sufficiently large but a fixed index k, and then you will just choose arbitrary large n, so you get n large enough. Therefore, when we compute fxn over g of xn minus b, we apply the triangle inequality, we'll get the first term plus second term and plus the final thing, sorry, not final thing minus b. It's less than epsilon. Right? So that's That's a proof. So this one is always less than epsilon, so we get this. Okay, so this part, this is a tricky process, very tricky, but we don't want you to invent this tricky process, but we want you to learn this tricky process. Next time, maybe you can learn to apply this trick to other computation. Okay, so you always create two indices. Those two indices both converge to approach infinity. One should be sufficiently large but fixed. The other one will be arbitrarily large in order to make the ratio 0. In order to make some ratio 0. So this is a very good trick. It's advanced trick, but you don't have to invent it, but you have to know how to apply it in your study. Right? Okay. This is a case when the a is 0 or infinity, but we always assume the point a is a fixed number, is a number. Now let's talk about case 3. This time the point a is infinity because a is an extended real number. Point is infinity. Still, we assume that a is past infinity. A is a past infinity. Okay, if a is a past infinity, then we choose a number c such that the open interval c infinity belongs to I. So it's approaching a. Okay, so for each y in 0, 1 over c, we set phi y to be f of 1 over y. Phi y to be f of 1 over y. We want to flip. We want to transform infinity to 0. Okay, 0 is the fixed number. We already handled the numbers. We want to transform infinity to 0. How do we transform it? Flip it. Okay, 0 and infinity, they are reciprocal to each other. In certain sense. Okay, phi of y is f of 1 over y, and the psi of y is g of 1 over y. Then phi prime of y, psi prime of y is equal to f prime of 1 over y negative 1 over y square, g prime of 1 over y negative y square. See, there's some symmetry here. So what we get is that let x be 1 over y, then phi prime of y over psi prime of y is f prime of x over g prime of x. Okay? And this phi and psi satisfy the hypothesis of cases 1 and 2 for this a equal to 0. In the case 1 and case 2, we get capital A equal to 0, capital A equal to infinity, but a is arbitrary point. This moment we only assume a is 0, and the interval I is from 0 to 1 over c. Right? Then we get, from the case 1 and case 2, we get the limit x approaches infinity, f prime of x over g prime of x. It is a limit y approaches 0 from right hand side phi prime of y to psi prime of y, right? From right side, because it's on the right side. And by the first and second cases, it is equal to phi of y equal to psi of over psi of y. Phi of y over psi of y. And this is exactly the limit x approaches infinity, f of x over g of x. So the third case, we actually don't prove anything. We just do a flip and apply the case 1 and the case 2. Okay? We flip and apply the case 1 and the case 2. So this is the proof of the L'Hopital's rule, and it highly depends on the what? The generalized mean value theorem, the Cauchy mean value theorem. So the mean value theorem is one of important theoretical theorem in the calculus, in the analysis. All right? Okay, so let's discuss example in the next video. Okay, so we finish this video, and we will continue the discussion of the standard example of application of a L'Hopital's rule in the next video. Thank you very much.